Actually, I think while we're recording, I am going to take the camera off and record my whole setup here, because it's so awful that I'm proud of even having tried to do a course with this arrangement. I should probably have tried to build something, but I'm better at sort of algorithm design than my father was a civil engineer. But so this is my drying rack. This is my chair, my other chair. This is the little camera. The laptop is sitting on top of what used to be a Mandarin box. And you have the phone keeping, oh right, we keep track of, we start the phone timer again. And my den, which has been converted into a lecture hall, very small lecture hall. I am so looking forward to having real classes again, where you have a blackboard, you have space, you can push the blackboard up, and you have another blackboard that's as big as this whole thing. That was algorithms. I can try. What do we not need here? We don't need this. Okay. Oh. What I should do is take a picture of this just to get it slightly higher resolution before I start erasing things. No, that's not great, but it'll do. Okay. Actually, I don't need to worry about taking a picture like this, because these are just the chapter headings. So, okay. How does caret subas work? So suppose you have some number, you have these two numbers, x and y, right? And you want to multiply x and y. And suppose that these are n-digit numbers. So n-digit numbers. So what we're going to say is this is x1 times b to the n over 2. Actually, I think this was an m at some point, right? Right, so if this is, if x equals 5, 1, 7, 4, 9, 6, 7, 2, and y equals 2, 3, 8, 5, 4, 4, and 8, 1, 4, right? The base, okay, if the base is 10, what would come next? Honestly, for me, after this course, I would take a short holiday. Maybe, like relax for a few weeks from other complexity classes. Okay, so first of all, we haven't seen everything. Okay. In divide and conquer, there's a classic algorithm called convex hulls, right? Where there are other algorithms, but it's classic. A domain, if you follow the link to the FFT lecture, and you click, then you have domain's other lectures. And he does the convex hull. So basically, a convex hull, you have a bunch of points, and a convex hull is a shape, the minimum shape. So you have to, sorry, it's convex. So let's put one there. Right. So it has to be. So it's the smallest convex shape that contains all of the points. Okay, so this comes up in lots of stuff. How do you find a convex hull? So the divide and conquer, I forget, this actually, the algorithm has a name, and I forget the name. But one of the things you can do is you have the points. Okay, well, you sort them by x-coordinate, and you split them, right? And if you have let's say that we've split them here. Let's not do that. I'm doing this because I actually really wanted to show this in this course, so I just didn't really have time because we were getting close, we were in divide and conquer, and I realized we spent a lot of time on divide and conquer. But that was because we had to do asymptotic notation as well, and we were sort of covering some of the basics are packed into divide and conquer, but it meant I didn't do this algorithm. So if you find the convex hull of this side and of this side, and then you say, okay, now how do you put those two together? Well, you can find here, you consider the lines and you walk around until, if you go any further over here, the line between this and this point intersects this shape. And then from here you walk around, so you start at the closest, and then you start walking around until if you walk any further on either side, so you're here, if you walk here, the line is going to intersect this shape. If you're here and you walk here, the line is going to intersect this shape. So you say, okay, I add those lines, and then this is the convex hull of the whole thing. So there's a nice divide and conquer that does convex hulls. We didn't do any computational geometry, I think. Did we? We maybe did. No, I don't think we did. So there are a whole, Domain is famous for this computational origami. It's fantastic. I can send you. I'm not wearing my. Oh, actually, I took it here. So I was wearing this when I went out this morning. So the conference is WADS 2009. So WADS, it has a terrible name, but it's workshop. It was originally Workshop on Algorithms and Data Structures. Now it's Symposium with Algorithms and Data Structures, and W doesn't stand for anything anymore. WADS 2009. So Domain is from Halifax. I think I said that before. He was a guest speaker at WADS 2009. So Meng, or Mung, if apparently that's how his name is supposed to be pronounced, he's actually running WADS here, WADS 2021, in a week or two, I think, at Dow. So anyway, at WADS 2009, Domain was an invited speaker, and he did this cool thing. He has a theorem that says, if you take a piece of paper, the plane, and you draw a collection of dots, lines, and polygons, he has an algorithm that will fold the paper and such that if you make a single cut, and then when you unfold it again, you've cut out exactly those dots, lines, and polygons. So and also he's got other variants, like you can draw a bunch of blue dots, lines, and polygons and green dots, lines, and polygons. He can find a way to fold it such that there's a blue line and a green line. If you cut the blue line and unfold it, the blue dots, lines, and polygons have been cut out. If you cut the green line and unfold it, the green dots, lines, and polygons have been cut out. So anyway, at the conference, he did this with a maple leaf. Like, if anybody has ever tried to cut out a maple leaf, it is not that easy. So he had a piece of paper with a drawing of a maple leaf with a bunch of lines on it, and with instructions of how to fold these lines, which became valleys and which became mountains. The valleys is when it's like this, and mountains is when it's like this. So how to fold it, and then there was one line, you cut that line, you unfold it, and you have a perfect maple leaf and a perfect silhouette of a maple leaf. And I can't usually get that kind of stuff to work at all, but even I can do this. So I still have the PDF lying around. I can post it on Brightspace. So computational geometry is tons of fun. We didn't do any of that. We didn't do, like 2019, I did a streaming algorithm for something called iceberg queries, and which it's got constant space complexity. We didn't do anything like that. I mean, no, the CLRS is huge, and there are all these other topics, so it has some computational geometry in there. We didn't do most of those. I don't think we did. Did we do any of them? We didn't do, apart from Huffman's algorithm, we didn't do data compression. Without getting, algorithms is a big field, and it comes up everywhere. I mean, nowadays everyone's like the algorithm, they're making movies about this. Most people who make the movies about it, although actually, yeah, okay, so this movie wasn't, I was going to say, just today I was reading something by Chazelle, who's a CS professor at Princeton. And if anybody's seen La La Land, it's directed by his son. Damien Chazelle is Bernard Chazelle's son. So actually, there are people in Hollywood, and also a bunch of, like, this guy who was a professor at Princeton, where Jeffrey Westbrook. So he wrote a really nice PhD thesis, graduated from a top school, became a professor at the top school, and then packed it in and went away to become a writer for The Simpsons. So actually there are people who are writing accurate, and I think I mentioned in one of the lectures that Sneakers, Leonard Edelman, was a consultant on Sneakers. So there actually are correct algorithm stuff. There is correct algorithm stuff in the movies. But although I think, so most people get the impression from media that algorithm means it's like spying on you software. I've never written any spying on you software. So okay, back to carrot soup. So okay, what can you? You can do a lot with algorithms. I mean, algorithms are how you do something and get a result that you're going to be sure is correct, and how you do it efficiently. So that's sort of how everything we can do. I mean, everything you do with a computer is sort of going to involve algorithms somehow. So that's why I think that's why I think this course is important. But okay, back to Karatsubas, because I have, so I think Westbrook might have also written for Futurama, and he wasn't actually the only one. There's a graph theory paper, which I've cited. It was Westbrook and, I forget the name of the other guy. And they both went to be writers at The Simpsons. So, and there's also, there have been things like you can get YouTube videos about the math in The Simpsons. Anyway, okay, Karatsubas. Because otherwise it's going to look like I'm trying to bluff my way out of doing Karatsubas algorithm. Okay. Okay, so we split each of these in half. B is equal to the base of our number system, let's say, is 10. So what is this? X, so x1, x0, y1, y0. So notice that this is x is x1 times 10,000, which is b to the 4. So this is n is 8, so n over 2 is 4. So it's x equals 5174 times 10 to the 4 plus 9672. That's just a dot, not a multiplication. Y equals 2385 times 10 to the 4 plus 4814. Now, what you would normally do is you'd say, okay, x times y is going to be x1 times b to the n over 2 plus x0, y1 times b to the n over 2. Why is that a capital? That's a small. That's a mess. To the n over 2 plus y0. So you normally do 4 multiplications. You do x1, y1, b to the n plus x1, y0, b to the n over, why do I keep making that a capital? N over 2 plus x0, y1, b to the n over 2 plus x0, y0, right? So you do this. So then, but we don't do that because that's 4 multiplications of n over 2 digit numbers. And that doesn't help us. Why is it b to the 4, where? Here? Okay, because notice that why is it b to the 4 and not 8? Okay, so this 4 gets left shifted n over 2 spaces, right? So it's this 4 in the whole in x. This 4 is not a 4. This is a 40,000. So here we're going to have 5174 times 10 to the 4 is 5174,0000. So if you take this and this, each of these is a b to the n over 2. So when you multiply b to the n over 2, b to the n over 2, it's b to the n. This one and this one, there's only one b to the n over 2. This one and this one, there's only one b to the n over 2. And then x0 times y0, there's no b to the n over 2. Okay? How much time? 5 minutes. Okay. So what we're going to do, to do Karasuba's trick, we're going to say, okay, z1 equals x1, y1. No, that's z2. z1 equals x1, y0 plus x0, y1. And then z0 equals x0, y0. But, so this is still 4 multiplications. But Karasuba's trick is to say, but this is equal to x1 plus x0 times y1 plus y0 minus z2 minus z0, right? Because what's that? That's equal to x1 y1 plus x1 y0 plus x0 y1 plus x0 y0, and then minus x1 y1 minus x0 y0. So this disappears, and this disappears. So it's x1 y0 plus x0 y1. So now we're going to do two additions, a multiplication, then two subtractions. So this is going to take only 3 multiplications. Now we do so maybe this is actually what the question was. So we're going to do the recursion where you can say, okay, can I write? Why break with tradition? I might go over time today as well on the last class. So T of n equals, well, what is the recurrence? The time for doing this multiplication, we're going to do, instead of one multiplication of 2 n-digit numbers, we're going to do 3 multiplications of n over 2-digit numbers, plus a bunch of additions and subtractions which take linear time. So this is going to be like a sum of n. So, like, okay, let's say, yeah, we worked this out in class. This is like 5, right? Some constant times n. I'm just going to say 5. Okay, in that case, what is A? A is equal to 3. B is equal to 2. F of n is equal to 5n. Okay, well, which case of the master theorem is this? Well, we have to look at log base 2 of 3 and compare it to f of n. And I forget which case this is. So the cases, remember, in the master theorem, the cases are, when you look at the recursion, the root is, most of the work is at the root, or most of the work is at the leaves. So the 3 cases in the easy version of the master theorem are either the weight is at the root, the weight is at the leaves, or the weight, you sort of, like, each level is equally weighted. So in this case, this is bigger than this, so it's going to be at the leaves, I guess. So anyway, it's going to be n to the log base 2, 3. Right, so we plug it into the master theorem, which I don't have in front of me, but as you may have seen on the exams from previous years, if I ask questions about the master theorem, I actually paste the master theorem there. So we're going to get O of n to the log base 2, 3. And then messing about, so this is getting rid of this b equals 10. That's just, yeah, okay, actually that's fine. We just leave it like that. Is that correct? That looks correct. Yeah, that's subquadratic. So that's like n to the 1.58 or n to the 1.85. I got that backwards on one of the assignments. See, that wasn't that bad. And I'm only 1 minute overtime. So the course is now over. Yay, I will never teach online again, I hope. Maybe I will, a little bit, but I hope never a full course. Okay, so thank you for being my class. Everybody who, no class on Wednesday, so that I'm gonna get my coffee table back. And good luck on the exam. And with fourth year, no, I guess it might be office hours. There's no tutorials because the last day of class is Thursday. So we can't, the exam period actually starts on Friday. So we can't have a tutorial. That's why everything is due on Thursday, because that's the end of the teaching period. Thank you for being my class, all brave 9 people who actually stuck it out. But the office hours, I think, yeah, the TAs could run office. I mean, it'll be a bit tight having the office hours on Thursday when, oh yeah, usually the office hours are on Thursdays and Fridays, right? I guess we could have office hours on Thursday and have the assignment due on Thursday night for like the absolute last desperate hope. Yeah. Okay, so that was algorithms. Good luck with fourth year graduation, your careers in computer science. If you're around, so somebody actually did say hi to me in the park. I just had been running and I was wandering on thinking about something, and somebody said, "Hi, Travis." So now I'm wondering, because I think I wrote on some assignment or something, say hi to me if you see me. So somebody did. So if that person sees this, hello. I was thinking about something else, so I didn't say hi back until they were also running, so they were past by the time I said hi. But yeah, if next year, if you're still in Halifax and you see me on campus, I probably won't know who you are because I've never seen any of you. But say hi. Okay. Cheers. That's it. If there are any other questions, I can hang around for a few minutes, but everyone is free to go. And the little camera will stop recording in a second. So, wait, how can we ask questions during the exam? Everything will be totally clear. I will be on, that's a good question. So there's a Splendus lockdown browser. I don't know if I'm going to bother with that, because you could always just have another laptop beside it, in which case the Splendus lockdown browser is pointless. Or actually, I mean, I can't lock your phone, and I'm not going to, so somebody I was talking to said that they actually dropped the course because it required this creepy spyware that, the thing, and the person said that he couldn't find out where the recording was stored, and there were very not great guarantees about sort of privacy protection and stuff like that. So, so I'm not going to do that. Yeah, so if I don't do the Respondus thing, then you can just ask me. I mean, if it goes from like 7 in the morning, or if I do this thing where I give you an extended time period, so 7 in the morning until midnight, I'm not going to be awake that whole time. I could ask the TA. This year, the first year I posted my phone number. I think I'm not going to do that this year. That was maybe a bad idea. Yeah, you can ask me by email. I usually check email. So that's it. I mean, if you do the Respondus lockdown browser, then you can't ask me by email. Well, you can by your phone. Okay. Yeah, we'll figure something out. I can always ask how people are doing.